In progress.
Good morning, sir. Good morning, Antonio.
Good morning. I don't know if you can hear me, but good morning.
Yeah, I hear you just fine. Okay, it appears I actually remembered to publish the lecture notes this time, so that's good. Okay. Okay, good morning, folks. I've got a few minutes past, so we should go ahead and get started. We've got a full hour today. The topic is very interesting and important about the fine and the hyperfine structure of hydrogen. I spent way more time than I probably should have going into the notes and preparing for this lecture. This is a subject that we could easily spend another week on by itself, but we're going to cover just the highlights of it today. So before we dive into all of that, let's tackle a couple of logistical issues real quick. Just an update on the count for the homeworks. The major point for you guys is that there is a cutoff on homework acceptance for full credit this Friday at midnight, because I plan to post all of the solutions automatically on Canvas at midnight. So you have all weekend and then the rest of next week before the midterm to use them as study material. So as of right now, I have 12 out of 14 submissions for homework 3, 5 for homework 4, and 2 for homework 5. All of these are due at the same time, last chance for full credit this Friday. So if you're behind on the homework, please do your best to catch up. Honestly, if I were in your shoes and I were behind on some of these homeworks, I would seriously consider skipping problem number 2 of homework 4, because it's straightforward, but that is a big time sink, and that is worth 10 points. So homework 3 is 20 points altogether, homework 4 is 20 points altogether, homework 5 is 10 points. So if I was deciding on where I should spend my last few hours, I would probably skip problem 2 and spend that time instead on homework 5. But you've got more chance to get your 10 points on homework 5 than on working through all of the maze of algebra associated with problem 2 of homework 4. So that is my recommendation to you if you're rushing to catch up. If you don't get something turned in, you can still turn it in after the fact, but you won't get full credit for it. I'll treat it like a correction, and you can get up to 50% of the missed points back, which in this case, 50% of a 0 would be 50% total coming back to you. So the plan is on Monday, we will go through the sample exam. I'm putting that together now. We will solve it in class so that you have all the indications about what's going to be on the exam and how to prepare for it. And then I'm planning on holding the midterm in class a week from today. That's Wednesday the 10th. I don't expect any major problems in terms of logistics for how to do the exam. So we've talked about this before, but just to remind you, I will set up the exam so that it appears on Canvas at the start of class. If you'd like to be here and take it in person, I will have paper copies, and you are welcome to solve it all on paper and give it to me if you prefer the old-fashioned way. If you prefer to take it remotely, you are welcome to do that. The exam is open notes, open textbook, open Wikipedia, but not collaborating with friends. So work by yourself, but all resources are available to you. I think that's it as far as logistics. Any comments, questions, or concerns from you guys? Okay, if not, then we'll discuss the midterm on Monday and we'll work through what you can expect from that. So like I said, there's a lot of material to discuss today in terms of the fine and the hyperfine structure. You can teach a whole spectroscopy course on this stuff. And we're just going to hit the most important physics highlights of it today. We're going to use the tools that we discussed last time, in particular, the conclusions we reached about degenerate perturbation theory. We said that perturbation theory relies on the assumption of a nice, smooth, analytic dependence on the coupling constant. And there are many ways that that can break. One of them is if you have non-analytic, non-perturbative effects. And one time you can encounter non-analytic effects is if you are trying to solve a perturbation which breaks a degeneracy. We talked about the example of spin-orbit coupling, which is exactly the fine structure of hydrogen that we'll be talking about today. If your non-perturbed Hamiltonian is just the Coulomb potential, and the fine structure, as we'll discuss, introduces an effective L.S coupling, this L.S coupling is off diagonal in the LZ-SZ basis, but it is diagonal in the total momentum basis J and JZ. So it matters which of these you use to do perturbation theory when you have a perturbation that breaks degeneracies. So if you start off with this LZ-SZ basis and you try to do the formulas for perturbation theory, bad things will happen. You'll get stick infinities, you'll get, so your energy denominator will be 0 because of the degeneracy. And when you try to do that, you'll end up with effectively non-analytic or non-perturbative effects in this basis. But that's something that you can get around by choosing a basis in which the perturbation is diagonal. So not all bases are created equal when you have a symmetry which is being broken by the perturbation. So the punchline on all of this is that we can still use the regular formulas of perturbation theory derived previously, but only in an appropriate basis for the perturbation which breaks the symmetry. Okay, let me show you something on Canvas very quickly before I dive into the new derivations. So as much as I would like to derive everything live for you guys today, there is just not going to be enough time for all of that. So what I have done is I have put some supplemental material on Canvas. All of the derivations are there if you would like to see all of the intermediate steps. But I think I'm going to have to resort to setting up the calculation in line 1 and then giving you the answer in line 2. And if you want to see all of the steps in between, they are there. So the lecture notes themselves are already like 15 pages. So obviously that's not going to happen. So we'll just hit the highlights from this. There are many steps in here that I will not have time to go through all of the algebra in detail. And in particular, there are some matrix elements that we're going to need. Matrix elements of 1 over r, 1 over r squared, and 1 over r cubed in the calculation of these corrections. This is a nice exercise which is in Shankar as one of the homework problems, exercise 17.3.4. There's some cool tricks that let you calculate these matrix elements by just rescaling parameters in the Hamiltonian. You can rescale the mass, you can rescale the charge, you can rescale the angular momentum. And by using the exact solution that you know for any mass and any charge and any angular momentum, you can immediately infer what these things are. So those details are here, but for our purposes today, I am just going to summarize them for you on the board now, and we will make use of them in the derivations. So when one calculates the expectation value of 1 over r, this is in the states NLLZ. What you get is 1 over n squared times the Bohr radius. And if I express this in terms of the fine structure constant, this is alpha E&m over n squared, mc over h bar. Likewise, 1 over r squared is 1 over n cubed L plus 1/2 Bohr radius squared. And this is alpha E&m squared over n cubed plus 1/2 n squared c squared over h bar squared. And the last one we're going to need is 1 over r cubed, which is 1 over n cubed L plus 1/2 L plus 1 over the Bohr radius cubed, which goes like the fine structure constant cubed. Alpha E&m cubed over n cubed L plus 1/2 L plus 1 times mc over h bar cubed. So when we start calculating the corrections coming from the fine and the hyperfine structure, we will need these matrix elements, so we will just take these and run with them. The important thing for starters is the power counting in terms of the fine structure constant, alpha E&m. Every time you add a mass dimension, anytime you add an extra factor of the Bohr radius, which are the natural units for these things, the matrix element goes down by a factor of alpha E&m. So alpha, alpha squared, alpha cubed. And they come with particular dependences on n and l. Okay, so without further ado, let's dive on into the fine structure and the hyperfine structure. So we're talking now about the splitting of the energy levels of the Coulomb potential. So this is the gross structure of the Coulomb potential. We found that the energy levels En were minus m e to the 4th over 2 h bar squared, going like 1 over n squared. It's interesting and useful to rewrite this in terms of the fine structure constant. If I write this in terms of alpha ENM, this is minus 1/2 mc squared, the rest mass energy of the electron, times alpha ENM squared, 1 over n squared. So just to remind you, the fine structure constant shows up in these electromagnetic units as E squared is alpha h bar c. So every time you have E squared, that becomes a factor of alpha ENM with a conversion factor h bar c. So Shankar has a really nice intellectual mnemonic that helps you interpret what this means, and this is going to be part of the origin of the various hyperfine corrections. This thing kind of looks like the kinetic energy. It looks like 1/2 mv squared, where v is alpha ENM times c, the speed of light. It's not literally this way, but it's an interesting and correct power counting interpretation of this formula. So Shankar's interpretation of this is to say that the relativistic beta factor, which is the velocity divided by the speed of light, is roughly alpha ENM. And so this is true for the ground state of hydrogen, that there are relativistic effects. They're small and comparable to alpha ENM. But when we start calculating the fine structure corrections, which are power corrections in alpha ENM, for consistency, we will also need to consider relativistic corrections that are higher order in beta, the relativistic velocity. So part of the fine structure will include not only relative order alpha ENM squared corrections coming from the electromagnetic interaction, from, let's say, quantum electrodynamics, but they will also include order beta squared, which, as this mnemonic helps you see, is also comparable to alpha ENM squared corrections from relativity. And so these two effects are what are going to lead to the fine structure of hydrogen. Overall, what this is going to do is it's going to take these 1 over n squared energy levels from the Coulomb potential and it's going to split them in ways that break the many-fold degeneracy of the Coulomb potential. So what we had for the Coulomb potential was an energy versus n that went like 1 over n squared. So we start off with a ground state down here, E naught. And then, let's see, the first excited state is 1/4 away from 0, and then the next one is 1/9, and so on. The energy levels went like 1 over n squared. Not only that, these energy levels were also highly degenerate. So this n equals 1 set of levels had L equals 0 automatically. So the ground state was non-degenerate in angular momentum. But this was without talking about spin. So if I include spin, this unique ground state in terms of N and L and LZ, has a twofold degeneracy from SZ. And if I start to think also about the spin of the proton, this is going to contribute to the origin of the hyperfine structure. That spin of the proton gives you another double degeneracy. So we will call this I sub Z. So this is spin of the electron. The electron is a spin 1/2 particle, and this I is sometimes used in spectroscopy to denote the spin of the proton. So what we will see is that the ground state will achieve a shift based on the total angular momentum J. From the fine structure, that will include the effect of SZ. Now the spin is not a spectator variable anymore. And then when we go to the hyperfine interaction that couples to the spin of the proton, that will actually split the ground state into total angular momentum states coming from the spin 1/2 of the electron and the spin 1/2 of the proton. Similarly, you had even more degeneracy for the higher states. So for n equals 2, we had 2 ladders of angular momentum. We had the L equals 0 S state, and we had the L equals 1 P state. This 2S level had one state in it, one state of angular momentum, LZ equals 0, but times degeneracies from the 2 spins. So times 2 for the electron spin SZ, times another 2 for the proton spin IZ. L equals 1 had the same energy as L equals 0, and it had 3 different LZ states. So there were three states. LZ equals +1, 0, and -1. And this triple degeneracy of LZ also gets multiplied by 2 for the spin times 2 for the proton spin. So overall for n equals 2, there were 4 degenerate states of L. 1 L equals 0 state, 3 L equals 1 states, and then also you have spin on top of it. So all of these fine and hyperfine corrections will start to interact with these different combinations of angular momenta and split the levels as well as shift them around. And we will calculate what those are. So this is essentially what we're trying to do. We're trying to take the major structure of the hydrogen spectrum coming from the Coulomb potential and include these kind of corrections. How big are the corrections? Overall, the effect from the fine structure is order alpha ENM squared. If alpha ENM is roughly 1/137, then a fine structure correction of order alpha ENM squared is overall a correction to these overall energy levels of what percent? 0.005%. So these are very small splittings of these overall energy levels. If the overall ground state energy was negative 13.6 electron volts, what we will find when we plug in real numbers for this is that the types of splittings that we get from the fine structure are hundreds of micro electron volts. That's how small these alpha ENM corrections are. The hyperfine corrections are even smaller than that because they couple to the spin of the proton. Hyperfine corrections coming from the spin IZ of the proton are the same order in alpha ENM, but suppressed by the proton mass. So this comes from the fact that the magnetic moment mu of the proton is the G factor of the proton. It's not 2 like for the electron, it's more like 5, but that's not a huge difference. Times the gyromagnetic ratio, which is E over 2 times the mass, and now this is the mass of the proton, times C, times the spin of the proton. And the fact that you have the proton mass in the denominator here rather than the electron mass is what leads to the hyperfine structure being even smaller. Even though it's the same order in alpha ENM, the hyperfine corrections will be order alpha ENM squared times electron mass divided by proton mass compared to the Coulomb levels. And that suppression factor by the mass of the electron divided by the mass of the proton makes it even smaller than the fine structure by an additional 0.05%. Little m divided by big M is roughly 0.05%. So the kind of corrections that we're talking about here are really high precision corrections to the atomic spectrum. The only other thing to point out before we begin the calculation is that the Coulomb energy levels are already order alpha ENM squared overall. These are relative corrections on top of that. So if the unperturbed Hamiltonian has energies that go like alpha squared, the fine corrections are going to go like overall alpha to the 4th. The hyperfine corrections are going to go like alpha to the 4th electron mass divided by proton mass. Okay, so that's the big picture of what we're after, these high precision corrections. Let's talk next about the physics that's going to generate them. Everybody good so far?
Yes.
All right, cool. All right, so the essential physics is going to be a magnetic coupling between different kinds of angular momentum. So the physical origin is going to be angular momentum coupling via the induced magnetic field. So for the fine structure, what we're going to get is a coupling between the orbital angular momentum L of the electron and the spin of the electron. And then we will also get a relativistic correction, which is independent of spin at the same order. For the hyperfine structure, where we include the effect of the proton spin, we will generate coupling between the orbital angular momentum of the electron, or the overall orbital angular momentum of the system, and the spin of the proton. So we will get L dot I coupling. So this is spin orbits with the proton spin, in contrast to the spin orbits coupling of the electron. And then we will also get a direct spin-spin coupling, I dot S. So in all of these cases, aside from the relativistic shift, which is independent of spin, in all of these cases, the essential mechanism is that one of these kinds of angular momenta produces a magnetic field. And the other kind of angular momentum interacts with that magnetic field. It wants to precess around it. And it has a certain energy of alignment in that magnetic field generated by the other kind of angular momentum. So let's talk about the L dot S coupling of the fine structure. So one has induced magnetic fields. So if my picture of the hydrogen atom is sort of a Bohr-like picture in the center of mass frame, I can sort of get my classical bearings by imagining that I have a fixed proton. It's so heavy that it's almost stationary, and I have an electron that's executing some sort of almost circular orbit around it. The electron has orbital angular momentum L, and that orbital angular momentum of a charged particle moving in a current loop in a circle produces a magnetic field. In this picture, it's a little bit weird to try and think about how does the orbital angular momentum of L produce a magnetic field, which I guess points this way. If I do my right-hand rule, I would say the angular momentum points up, but the charge of the electron is negative, so the magnetic field that it produces will point down. That magnetic field of the electron will interact with its spin, S. And I'm going to have some kind of minus mu dot B coupling between the magnetic moment associated with the spin of the electron and its own magnetic field. You can sort of get a better grip on what this looks like if you change your picture to the rest frame of the electron instead of that center of mass frame where the proton is stationary. If I now imagine that I'm sitting on the electron and the electron is the stationary one, instead of the electron moving in some counterclockwise orbit, now the proton is moving in some clockwise orbit. And so now the orbital angular momentum of the electron is now converted to the orbital angular momentum of the proton. So now I would have orbital angular momentum L, which is pointing down. The proton is positively charged, so that will produce a magnetic field pointing down. That's good that the magnetic field agrees between these two frames of reference. And in the presence of that magnetic field B, which in this picture we imagine is coming from the proton, now I have the spin of the electron S, which wants to align with that magnetic field. So we will set up the calculation of what this magnetic field looks like, and that will be mostly correct up to a factor of 2. The factor of 2 is called the Thomas factor, and it's telling you that this changing of reference frame is cheating. Really, this is a non-inertial reference frame, and it's moving relativistically at order alpha E and n. So a correct treatment that will give you all of the factors of 2 requires the Dirac equation and the full treatment of relativity, but you can understand the physics of this origin without that. So we're going to set up the L dot S coupling with that rightmost picture in mind of the electron sitting stationary and the proton orbiting around it. So the magnetic field of the proton's orbital motion So the magnetic field B is equal to the charge. The charge of the proton is plus E. Its velocity is minus V over C. V is the velocity of the electron. And I imagine moving to a frame where the electron is at rest. Now the proton moves with the opposite velocity minus V. Let's see. Cross R over R cubed. So if I plug all this in, I get minus E over C V cross R over R cubed. I multiply and divide by a factor of the mass, and I turn this into linear momentum mv. And I turn P cross R into angular momentum L. So overall, when I do that, I get a relative minus sign, E over MC L over R cubed. So this is our picture of the effective magnetic field induced by the motion of the proton. Yes, sir.
Which M's are you talking about?
Right now, this M is only the electron mass. It's only when we talk about the hyperfine structure that we will introduce the proton mass.
And a numerator?
Yeah, I'm multiplying and dividing by a factor of the mass.
Okay.
So that I get mv is the linear momentum of the electron that we usually talk about being L. So I want to express this in terms of the electron degrees of freedom, but I'm cheating by trying to do it in the rest frame of the electron. Okay, so if the magnetic field is something which is proportional to 1 over R cubed times the angular momentum L of the electron, I know the energy of alignment of any magnetic moment in that external magnetic field. Energy of a spin in a magnetic field we said that Hamiltonian associated with the alignment energy, so this is going to be the spin orbit coupling, is minus mu dot B. This mu is the mu of the electron, so I'll put that little e here. The spin of the electron is related to its magnetic moment by the G factor and by the gyromagnetic ratio. So the G factor of the electron is almost 2, times the gyromagnetic ratio is Q over 2mc. And Q, for the electron, that charge is minus E. Remember that that is negative. Let's see, and then the spin of the electron is S dot B. So when I put all these factors together, I now get a positive E, negative, negative, and that multiplies this one. I get E squared over 2 M squared C squared with a factor of G from the electron G factor S dot L. And again, if I convert from E squared to alpha H bar C, then the interaction itself is G alpha EM H bar over 2 M squared C. Yes. Oh, and I forgot the 1 over R cubed. So this gives me L dot S over r cubed. H spin orbit. Right. So, okay. If I plug in 2 for the electron G factor, then this would cancel this 2 and that 2, and I would get alpha H bar over m squared C. That answer is almost correct, but it misses a factor of 2 because of this cheating from going to the rest frame of the electron. A more correct treatment would give me an extra factor of 2 here. So I'm going to write this as G over 4. If you plug in 2 for the electron G factor, then this is approximately alpha ENM H bar over 2 m squared C. L dot S over r cubed. Okay, so this factor of a half is called the Thomas factor. I have to wave my hands at this point, but a correct treatment involving the Dirac equation will produce it naturally. All right, so we would like to calculate the shift in first order perturbation theory of the Coulombic energy levels due to this spin orbit interaction. So the formula that we've written before is that first order energy shift, I'll write as GE1 spin orbit. This is the matrix element in the unperturbed states, NLLZ of that correction, H spin orbit, NLLZ. So this is the part where we have to worry about degenerate perturbation theory. This basis set is off diagonal in LZ and SZ. So maybe let me add that SZ variable in here. LZ, SZ is not a good basis to try and do perturbation theory for this L dot S coupling. But we already know the solution. We need to just change basis using Clebsch-Gordon coefficients to the total angular momentum basis. NL, if you like, S, this total spin quantum number is still conserved. The relevant part is JJZ. GH spin orbits, NLS, JJZ. The reason that this thing is diagonal here is because that L dot S coupling can be written as 1/2 L plus S squared minus L squared minus S squared. So this is 1/2 J squared minus L squared minus S squared. So if I take that product and I open it up, I get a perfect square of L, a perfect square of S. I subtract those off. The part that I want is the cross term, L dot S. That's left over inside these parentheses, and I divide by 2 to give me L dot S. So the natural basis for describing the impact of the fine structure L dot S coupling is the total angular momentum basis J. In terms of the total angular momentum, J equals L plus S. So this is electron total angular momentum J equals L plus S. In this basis, the energy shift is GE1 spin orbit equals, I had a whole bunch of coefficients out front, G alpha ENM H bar over 4 electron mass squared C squared. And now I have expectation value. The relevant part of this is J, Z, and N. And I have L dot S over R cubed, N, J, Z. So the L dot S piece we express as here. So I write this L dot S piece as 1/2 J squared minus L squared minus S squared. These states are eigenstates of all of those quantum numbers. So I get H bar squared over 2 J plus 1 minus L plus 1 minus S plus 1. The spin is 1/2. So I have to keep L arbitrary and J arbitrary, but this number is just 3/4. H bar squared over 2 J plus 1 minus L plus 1 minus 3/4.
Is the G in the, I guess in front of the product there, is that the lambda factor G or the correction G, the coupling constant?
Confusion here. This G is the lambda G factor G equals 2. This G was the G we were using for power counting and perturbation theory.
Okay,
so
just making sure.
Question today, I should leave this one off to avoid any ambiguity here. This one was just around for our power counting purposes to help us keep track of first and second order perturbation.
Okay.
Thank you for the question. All right, so when I plug it all in, that spin orbit shift at first order, now dropping the G on the left-hand side to avoid confusing people further, is the lambda G factor alpha EM H bar cubed over 8 N squared C squared. I have a spin-dependent factor, J plus 1 minus L plus 1 minus 3/4 times the expectation value of 1 over R cubed in these states. This is the first instance where I needed those matrix elements. So if I plug in what I got from that computation, which is on Blackboard or Canvas, this matrix element of 1 over R cubed is alpha ENM cubed over N cubed L plus 1/2 L plus 1 times the dimensionful factor MC over H bar cubed. All right, so I plug in all of the numbers, and what I get is 1/4 MC squared alpha ENM to the 4th divided by N cubed, and then when I combine together the L dependence here and the L dependence there are exactly 2 outcomes. L plus 1 plus 1/2 if J equals L plus 1/2 or negative 1 over L plus 1/2 if J equals L minus 1/2. So at this level, the answer is kind of messy. It will clean up a bit when we add in the relativistic correction at the same order. So what you're seeing here is you get a level splitting. We have L dot S coupling. So if you had your hydrogen spectrum with just the Coulomb potential, and you pick, say, the 2p state out of this, having L equals 1, you have L equals 1 and you have spin equals 1/2. The fine structure correction, that spin orbit correction, is diagonal in the total angular momentum J. So you have to take these 2 angular momentum and ask what combinations can you make out of it. And if I take any L and I add spin 1/2 to it, I can either get L plus 1/2, which in this case is 3/2, or I can get L minus 1/2, which in this case is 1/2. So what this is giving us is a level splitting of that 2p state. You get a positive shift in this case. That's going to be the J equals 3/2 piece. And you're going to get a negative shift in this case. That's the J equals 1/2 piece. This will all be a little bit cleaner when we add in the relativistic correction at the same time. But what you're seeing out of this is that you get a correction which is overall alpha E and m to the fourth, and a level splitting that differentiates between the large value of j and the small value of j at a given level. Is this part okay? Okay, the correction coming from the relativistic kinetic energy is simpler because it is spin independent. So normally we write the kinetic energy as kinetic energy equals p squared over 2m. This is not exact. This is only true if the velocity is much less than the speed of light. If the velocity is not negligible compared to the speed of light, we have to instead use the relativistic formula E squared is pc squared plus mc squared squared. Once your kinetic energy starts to become comparable to the mass energy, the rest mass energy, you have to include both contributions on an equal footing by the Einstein relation of special relativity. This is the total energy. To get the kinetic energy, I have to take the total energy and subtract off the rest mass energy. So the kinetic energy, or I guess T is what we've been calling it. The kinetic energy in a relativistic setup is that energy minus the rest mass energy, which is square root pc squared plus mc squared squared minus mc squared. If I take this square root and I expand it in a Taylor series, assuming that pc is much less than mc squared, then I recover this original non-relativistic kinetic energy. What we're after is the first correction to that. So what I do is I write the kinetic energy as mc squared times the overall 1 plus p squared over m squared c squared to the 1/2 power minus 1. And I use the binomial series or a Taylor series to expand this. P squared over m squared c squared much less than 1. So when I open this thing up, what I get is p squared over 2m minus p to the 4th over 8 m cubed c squared, plus corrections that are order beta to the 6. So this quantity here is the non-relativistic kinetic energy. It is quadratic in the velocity. Once you start to become high enough in energy that you have to pay attention to the square roots, your energy doesn't just grow like momentum squared. It sees the fact that you're curving that dependence downward because of the square roots. You get a negative correction to the kinetic energy that goes like p to the 4th. And this truncates the series at order p to the 6, or that's equivalent to the relativistic velocity beta being beta to the 6. So this is the correction to the kinetic energy. So we want to work out what is the correction coming from this Hamiltonian, let me call it kinetic, minus p to the 4th over 8 m cubed c squared. So compared to the angular momentum case, this one is nice because it's a simple scalar. You can solve this in any basis you want. It doesn't care about L or S or anything. All we need is that matrix element of p to the 4th in the relevant states. So the first order energy shift due to the relativistic kinetic energy is the expectation value in the hydrogenic states NL/LZ. Spin is irrelevant for this. P to the 4th over 8 m cubed c squared with a minus sign. I guess this is my first order shift due to the kinetic energy. So the constants are irrelevant. How do I get the fourth order the p to the fourth matrix element, I can do that by, let's say, pulling out the overall constants, 8 m cubed c squared, and I'm going to multiply and divide by 2m squared. So that I can write this as p squared over 2m squared. This part occurs in the Hamiltonian. So overall, let's see, this is 4m squared, so I get minus 1 over 2mc squared. This piece is the original Hamiltonian plus the potential energy. Since the Hamiltonian is p squared over 2m minus e squared over r, I can substitute it the other way to replace for p squared over 2m. I know what the energy is in each one of these states, and then when I open up the square, that's going to give me averages of 1 over r and 1 over r squared. That's where I'm going to need the other pre-calculated matrix elements. Okay, so when I open up the parentheses, I get the first order correction from the kinetic energy is minus 1 over 2 mc squared times en squared plus 2 en e squared times the expectation value of 1 over r plus e to the fourth times the expectation value of 1 over r squared. And when I plug in for what each of these matrix elements is, I do some algebra and I get minus 1/2 mc squared alpha en to the fourth, and the overall correction is 1 over n cubed L plus 1/2 minus 3 over 4 n to the fourth. Okay, so now I have both pieces of the fine structure. The relativistic kinetic energy correction, which as advertised enters as order alpha en to the fourth. So this is of the same order as the higher order in QED spin orbit coupling effect that we calculated first. All right, so the total fine structure splitting, total fine structure corrections. First order energy in the fine structure is defined as the first order correction from spin orbit coupling. This is the L dot S plus the first order correction coming from the relativistic kinetic energy. When I add the two together, the N's and the L's just so happen to add together in a simple way. And what I end up with is minus 1/2 mc squared alpha en to the fourth over n cubed 1 over j plus 1/2 minus 3 over 4n. Before we had all of this annoying, complicated L dependence, and different cases depending on whether J was L plus 1/2 or J equals L minus 1/2. All of those differences come out in the wash. If you calculate both of these terms for either case, you find that this formula works for them both. Includes both J equals L plus 1/2 and J equals L minus 1/2. If you want to see how the algebra works out, it's all there in the notes that are on campus. Okay, there's one other comment to make at this point, which is that has happened as far as the spin orbit coupling. That L dot S coupling is not valid for L equals 0. Obviously, there is no spin orbit coupling if there is no orbital angular momentum. But that formula still is correct anyway, even for the L equals 0 state. So this is for the S states. The formula is still correct anyway, even for those states, because of another relativistic correction that we have not discussed explicitly called the Darwin term. The Darwin term is a relativistic correction that enters something proportional to a delta function. So it's a delta function that measures how much of the wave function is at the origin, on top of the proton. So it really is a contact interaction. That shift only affects the S states. If you have any amount of angular momentum, the Darwin term does not contribute. And it just so happens that the Darwin term adds exactly the same correction. So the bottom line is this for all of your states, even the L equals 0 states. But one should be clear that a cheat was used in deriving this L dot S formula without admitting that it does not correctly apply to the S wave states. Okay, I want to give you a couple of numbers associated with this. And I want to show you a picture associated with this before we move on to the hyperfine structure. So if I calculate the level shifts for n equals 1, the ground state of hydrogen, we had L equals 0 and we had S equals 1/2. There's only one way that I can add together 0 times 1/2. I must get J equals 1/2. So this state is an S wave state whose total J value is 1/2 coming from a spin doublet state. So in modified spectroscopic notation, the state is written 2s 1/2. If I plug in here J equals 1/2 and N equals 1, the energy shift that I get, E1 from the fine structure for N equals 1 is negative 181.3 micro electron volts, compared to the ground state energy of negative 13.6 electron volts. So very small corrections. N equals 2, there are two effects. At n equals 2, we have either L equals 0, S equals 1/2, or we have L equals 1, S equals 1/2. L equals 0, S equals 1/2 can only create J equals 1/2 when I add the angular momentum. This is another 2s 1/2 state. When I add together 1 and 1/2 angular momenta, there are two possible outcomes. This is going to give me a level splitting. I can get J equals 1/2 or J equals 3/2. This is going to give me a doublet P wave state with angular momentum 1/2 or a doublet P wave state with angular momentum 3/2. This will split the N equals 2 levels due to the fine structure. So if I plug in for these energy shifts, what I find is that for J equals 1/2, it doesn't matter whether it's the S 1/2 combination or the P 1/2 combination. The fine structure correction to these states is the same, but it's different from the fine structure correction to the 2P 3/2 state. So this is the 2S 1/2 or the 2P 1/2 states. The energy shift that I get is negative 56.7 micro electron volts, as opposed to for J equals 3/2, which is the 2P 3/2 state, that fine structure shift is negative 11.3 micro electron volts. So let me share screen for a moment and show you a picture of what this looks like. That is this. So this is a plot that I stole from Wikipedia. It's showing you the contributions to the fine structure. This first column here, okay, so the first column is the bare unperturbed Hamiltonian, and this is the N equals 2 state. This one is the level shift including only the relativistic kinetic energy effect. This one is including all of the fine structure effects, the relativistic kinetic energy and the spin orbit and the Darwin term. So what this is giving you is a splitting of the N equals 2 states into the 2P 3/2 and the 2P 1/2 and the 2S 1/2 states. This one is 11.3 micro electron volts below the unperturbed energy. This one is 56.7 below the unperturbed energy. So this is how this L dot S coupling splits the levels based on whether total J is 3/2 or total J is 1/2. Okay, that is the fine structure. In the 15 minutes that are left, I want to say a few words about the hyperfine structure because, was there a question? Yeah, okay. Because this is of great historical and fundamental importance for humanity. Okay, for the hyperfine structure. Again, this is an interaction which is mediated by a magnetic moment that is coupling to the spin and the orbital degrees of freedom. Now my picture is I have the proton and my electron is moving around it. Now I include the effect that the proton has its own magnetic moment. It has a spin I, and that spin I produces a magnetic field. So this is the magnetic field B generated by the proton spin. And in the presence of that magnetic field generated from the proton, which is much weaker than the magnetic field generated by either the orbital motion or the spin of the electron, that generates more little splittings from the coupling of the electron spin S and the electron orbital motion L, coupling to that magnetic field B generated by the proton. So the first step is to calculate the magnetic field coming from the proton. So the magnetic vector potential coming from the proton is A equals mu, the magnetic moment of the proton, cross product with the gradient of that 1 over r potential. There's a minus sign here. And in terms of this, you can calculate the magnetic field. B is curl of A. Calculating this curl is a non-trivial exercise because there are delta functions that start to show up everywhere. So you've got to be very careful in how you take that curl. After doing some careful algebra, what you get is the ith component of the magnetic field is the g factor of the proton, Gp, times E over 2. This is capital M, the mass of the proton, times C. And then what you get is the quadrupole tensor, Qij, minus, let's say, delta Ij, grad squared 1 over r. Here. Let me do it this way. Plus a pi over 3 delta ij delta function of r. And so this is multiplying the spin ij of the proton. So there are two effects that come out of this, and separating out the quadrupole tensor from the diagonal piece, which looks like L dot I or I dot S, is tricky. This quadrupole tensor Qij is the traceless combination 3Ri Rj minus R squared delta Ij over R to the fifth. So trust me when I say that there's a significant amount of algebra in starting from this vector potential, taking this curl, carefully separating out the trace piece, which generates this delta function from the Laplacian of 1 over r, and leaving the traceless quadrupole tensor, which is left. Once you have the vector potential and once you have the magnetic field generated by the proton, then you can couple the electron degrees of freedom to it. So there is the hyperfine spin orbit coupling. So this is L dot I, hyperfine correction. This one comes from E over MC P dot A. This comes from the minimal coupling of the electron motion to that vector potential A. When I plug in that vector potential, what I get is positive G proton alpha ENM H bar over 2 little m, the electron mass, big M, the proton mass, times C, L dot I over R cubed. So this is one effect. This is the coupling of the electron orbital motion to the spin of the proton via the induced magnetic field. The other one is the spin-spin coupling. So I'll call this S dot I coupling. That comes from mu dot B, electron magnetic moments in this magnetic field. And that's going to give you this whole tensor combination. So this is minus mu of the electron dot B, with that being B. And when the dust settles, I get the G factor of the electron, the G factor of the proton, alpha E and M over 4 electron mass, proton mass times C, electron spin, proton spin times that tensor combination. Qij plus 8 pi over 3 delta ij delta function of R. So these three effects, the quadrupole piece, the contact piece coming from a delta function, and the spin orbit coupling are what constitute the hyperfine structure. The hyperfine Hamiltonian is that spin orbit piece, L dot I, plus the quadrupole piece, plus the contact piece. This one is the quadrupole piece. And this one with the delta function is called the Fermi contact term. Working out the full level splitting coming from all of these effects is something way beyond the scope of this course. But the most important piece is the splitting that happens to the ground state. So that ground state was n equals 0, L equals 0. We had electrons spin 1/2. Altogether, this gave us J equals 1/2 for the ground state at the fine structure level. Now, when we add in the presence of the proton spin, I equals 1/2, we are going to now have an addition of angular momentum problem between the spin 1/2 coming from the electron and the spin 1/2 coming from the proton. In general, you have a complicated Hamiltonian to include. But in the ground state, L equals 0, we don't get a contribution from the spin orbit part. The quadrupole piece changes angular momentum by 2 units. It's a spherical tensor of rank 2. So this one only shows up at higher orders in perturbation theory. And the only correction which is responsible for splitting the ground state is the contact term. That's this piece here involving the delta function at the origin. So the hyperfine structure of the entire spectrum is very complicated, but the splitting of the ground state is simple. If I just pick out that contact term, that piece was G proton, alpha E and M, H bar. H bar? Did I drop the H bar? I do not have an H bar. I think I should have had an H bar. Okay, there may be an H bar missing there. There's definitely an H bar here at the level of the spins. Yeah, it's got to be an H bar there. okay, over little m, big MC. The constant factor overall is 2 pi over 3. And then one has I dot S, delta function of R. So let's calculate the first order splitting in perturbation theory due to this contact term, the spin-spin interaction in the ground state. So this is the fine structure correction at first order in perturbation theory to the ground state. So this is 2 pi over 3 G proton, alpha E and M H bar, little m, big MC, times expectation value in the state 1, 0, 0, I dot S, delta 3 of R, 1, 0, 0. So again, this I dot S coupling is off diagonal in a basis which separately has the proton spin and the electron spin. It is only diagonal in the total angular momentum. For whatever reason, the spectroscopists call this F as the total orbital plus electron spin plus proton spin piece. In this ground state, L is equal to 0. So it's really just the 2 spins. 0 in ground state. So as before, we convert from I dot S into the total angular momentum. I dot S is 1/2 I plus S squared minus I squared minus S squared. This is 1/2 F squared, the total angular momentum, minus I squared minus S squared. When I sandwich this between total angular momentum states, so I get energy shift due to the hyperfine structure at first order. All right, the 1/2 cancels the factor of 2, so I get pi over 3 G proton, alpha E and M H bar over little m, big MC. So times now, this is the, let's say, N, F, FZ states. F squared minus S squared minus I squared. Delta 3 of R, N equals 1 for this treatment. So the angular momentum part of this is going to give me H bar squared F times F plus 1 minus S squared is going to give me 3 over 4. I squared is going to give me another 3 over 4. And then the spatial part that I'm left with is that expectation value of the delta function. So this is just in coordinate space, integral d3r, the ground state wave function psi 1, 0, 0 squared times the delta function. This is just equal to the value of the wave function squared at the origin. Okay. Let's get this energy. Okay. So when I plug it all in, I get the hyperfine corrections to the ground state are pi over 3 G proton, alpha E and M H bar over little m, big MC, F plus 1 minus 3 halves times the wave function at the origin, psi 1, 0, 0 at the origin squared. I look up in the textbook, what is the wave function? And I plug in R equals 0. And I just get 1 over pi times the Bohr radius cubed, which is 1 over pi times alpha ENM mc over h bar cubed. I plug in for what these overall spin coefficients can be. So I had spin 1/2, and I'm adding to it proton spin, I equals 1/2. So there's 2 possible outcomes. I can get F equals 1, an angular momentum 1 ladder, or I can get F equals 0, a singlet state. So if I evaluate this for either F equals 1 or F equals 0, at the end of the day, what I get is 23. The pi cancels the pi, so I just have G proton over 3 mc squared alpha ENM to the 4th little mass divided by big mass times either plus 1/2 or F equals 1 or minus 3/2 or F equals 0. So this is the hyperfine splitting of the hydrogen ground state. You have some energy scale, positive correction for total angular momentum F equals 1, negative energy correction for F equals 0. So this makes the total F equals 0 state the lowest ground state of the hydrogen atom, including the hyperfine interaction. The last comment to make is about the magnitude of that energy difference. You have now the F equals 1 state and the F equals 0 state have a different energy. And the energy of a transition from one to the other is a fundamental constant of nature, which is hugely important for astrophysics. I will just quote the answer, but you can plug in the constants and see what you get. So the energy difference of the hyperfine splitting, that is the energy of the F equals 1 state minus the energy of the F equals 0 state. This combination gives me 2/3 G proton mc squared alpha ENM to the 4th electron mass divided by proton mass. This energy is 5.9 micro electron volts. If you convert this from the energy of the difference to the wavelength of a photon emitted or absorbed during that transition, this gives you lambda equals 21 centimeters. In astrophysics, this 21 centimeter line is everywhere in the universe because the hydrogen is the most abundant element in the universe. And this level splitting is a fundamental, very precise, calculable quantity in the splitting of the lowest levels of the energy. So the last thing that I want to show you is just to share screen. Here we go. So the image on the right is an image of the galaxy taken by the WMAP satellites of the 21 centimeter line. So you can see the abundance of exactly this transition, which we can calculate from first principles in quantum theory and see reflected all over the universe to measure the abundance of hydrogen. This was considered a universal standard of length, so universal that it would transcend species. For this reason, this transition was used as the unit of length on the Pioneer and Voyager plaques, so that when this was sent out into deep space, if aliens ever encountered it, they can understand, even without knowing anything about humanity or human length scales, they can understand the splitting of the hyperfine transition and the corresponding unit of length that comes with it. So the Pioneer plaque measures the typical size of humans and distances from galaxies in units of this 21 centimeter line. So I don't know. When I did this calculation, I found it very profound to think that this was a major achievement of humanity that is sitting on a plaque in space, flying out farther than any other object ever created by mankind, as a testament to how deeply we understand the universe in a fundamental way that could connect with other alien life someday. Okay, that was a lot very quickly. hopefully at least you get the concept of what the fine and the hyperfine corrections are and how one uses perturbation theory to split the corresponding energy levels. Thank you for sticking with me on this. Next week we will review and we will have the midterm. Any questions or comments? All right, thank you guys very much.
Thank you.
Whew.